G'day. So welcome to today's Mathematical and Computational Sciences seminar by our own Dr. Quanling Gang from Computational Sciences. We'll be talking about superparameterisation of Arctic sea ice floes. So, if I do a brief bio, he's a lecturer in the School of Computing, born in China, moved to the USA to study mathematics, and graduated with a PhD in computational mathematics on finite element analysis. So he will also have could also perhaps sit within that Mathematical Sciences Institute. He joined Curtin University in Australia as a research associate and mainly contributed to the development of isogeometric analysis, and was a short-term visiting scholar at INRIA in Paris, AGH University of Science and Technology in Poland, and École de Pointe Paris Tech, USTC and others. In 2020, he joined the Department of Mathematics at the University of Wisconsin-Madison, as a Van Vleck visiting assistant, and worked on modeling and prediction of Arctic sea ice dynamics, which I'm hoping he will talk to us about today. So there's also some food available over there. Please be my guest. Thank you, Quanling.
Thank you, Matthew, very much for the introduction. Thanks everyone for coming. Also for people in Zoom, thanks for joining. Let me first acknowledge that this is a joint work with Professors Nan Chen and Sam Stechmann from the Department of Mathematics at the UW-Madison. As Matthew said that before joining, I was a part of this group here in the applied math community. Oh, sorry, why I can't use this here. Let me do this. Okay, so the outline of my presentation, I will start to give some quick facts about Arctic sea ice, or more generally, the sea ice, and then talk about some background on sea ice models, in particular the continuum model and the particle models. And then my main contribution is on this multiscale modeling. So we worked on the superfloe, parameterized the system, multiscale particles for the modeling, and then developed a particle continuum model. So the first model is on the probability density functions, and I mainly worked on the second one, which is towards the atmosphere ocean ice coupling. So what is sea ice? So sea ice is frozen ocean water. It forms, grows, and melts in the ocean. So particularly it interacts with ocean and atmosphere. So on the ocean side, it has the interaction with the ocean current, like ocean velocity, and the salinity and the temperature. In particular, salinity and temperature will affect the melting and freezing point of the sea ice. So in particular, for example, if we have a high salinity, the ice is more easy to grow. And the atmosphere side, it interacts with the wind and also the precipitation, which includes the rain and precipitation of snow, and also the sunlight, which impacts the temperature. And then it has different shapes of sea ice floes and typically covered with snows. If we do a simple Google search, look into the images, so we can see that there are lots of different shapes. So here, for example, we have polygonal shapes, polygonal ice. So this is an Arctic region, sorry, Antarctic region. And then there are some pancake shapes of the floes. So this more like a disc. And then some floes covered by snows. And then why it is important? So it is important because that it keeps the polar region cool. It also helps moderate the global climate. So in particular, if we look at this figure, it shows that its ice reflects about 85% of the sunlight. And then the other ones will be absorbed. Certainly, there's a portion maybe if covered with cloud, and then there's some other refractions. But without cloud, it's roughly like this percentage. And if there's no ice, then the ocean will absorb 93% of the sunlight. So if without ice, then it will warm up with the ocean. So they, let me go to some quick facts. So the very first one is that we are losing the ice. So in general, globally, like both in the Arctic region and also Antarctic region. So in Arctic region, in particular, if we look at the Greenland, so over the last 20 years, from 2002 to 2020, about 20 years, we observed that the total mass is continually decreasing. So in average, is about like 279 gigatons per year is like reducing this amount. And then Antarctic region, it also the mass is reducing about 149 gigatons per year. And then this leads to the global sea level rise. So I will go to a little bit more statistics in that in a second. So when I was making this slide, a news popped up to me, and this news is from last week, it's January 25th. It says that Greenland is with unusually extensive melting of ice sheet, boosting the sea levels. So it's accelerating the sea level rise. So this Greenland region has the world's largest glacier, and its melting ice is the top annual contributor to the global sea ice rise. And then this sea ice rise kind of determine the fate of coastal cities, such as like Hong Kong, Miami, or other cities like in Holland. Number two, the fact that this sea ice area, the annual area or minimum area is decreasing. And this means that more sun ice will be observed by the ocean. So over from the 1978 to basically last year, the Arctic sea ice minimum area is continuously like decreasing. So this contributes to the third fact that global warming. So this plot is from the Berkeley Earth. It shows the annual average temperature anomalies over this years, like 1850 to 2020 roughly. And then this blue dot shows the annual average, where the red curves shows the 10-year moving average. And then from this figure, we observe that 2016 is the warmest year, basically this dot here. And then 2019 is the second warmest. This is about roughly 150 years ago. And there's the long-term trend is, shows that roughly in about 30 years or so, the temperature would increase by 2 Celsius. So far it has been increased about 1.3. It has the global warming, this issue becomes more obvious. This global warming leads to the global sea level rise. So if we take a look at this figure, so the global sea level rise has 2 contributions. One contribution is from the seawater expansion from the ocean warming. This yellow line indicates that. And then another contribution is from the melting of land-based glaciers like the Greenland, and then this melting of this ice sheet. So this is indicated by the blue curve. So in average, it increased this sea level rise about 3 millimeters per year. So this seems not much, but if say over 100 years, this is roughly like 3 meters. And also we observe that this is accelerating. So this slope becoming larger and larger. So this can be an issue in 20 years or 50 years or longer. So let's look into the models. So the first model of describing the Arctic sea ice is given by Hilber in 1979. So where he described the Arctic sea ice as a material, in particular, It described as a viscous plastic, and they modeled this as this PDE. So here, the edge represent like the thickness of the Arctic sea ice, and then V velocity, and the A is like the kind of concentration or the area ratio. And then he tries to understand what is like the stress tensor on this plastic or this sea ice, and what is the rheology here, trying to capture the main features of the Arctic sea ice. And then along this line, in 1997, another continuum model developed based on this work, and they adding more features, which described as elastic viscous plastic for the Arctic sea ice. And then later on, it described as Maxwell electro-brittle model, but they all are continuum models. So I think I skipped one slide here. Yeah. So now with the help of the satellite images, then we observe notice the particle feature of the sea ice. So here, this is roughly image showing in like February or March, showing that the sea ice is starting melting at this time of the year. And then we see the like a little bit of coordination here. This is Alaska, this is Canada, this is Banks Island, and this is Arctic Sea. And then this is the sea ice where there is a Beaufort Sea. In this region, usually during this season, like in February or March, there is a gyre, which is called the Beaufort gyre. It's a huge gyre circulating in the Arctic region. This gyre drives the ice to fracture, and we start to see this fracturing behavior. And then if we zoom in, then we see that we see some like fogs, which would bring us difficulties when people try to do the data assimilation, which is a kind of a tool trying to understand the ocean currents, like because we cannot see the ocean current directly. We can try to use the sea ice model, try to recover the ocean currents, how it behaves, in particular in this Beaufort gyre region. And then in larger scale, so this figure shows that at a certain time, the fractures develop everywhere in the Arctic Sea. So we see different scales in this region. And then this brings us that to consider in the particle model, where we need to take the different scales into consideration whenever we build this model for the Arctic sea ice. So we've been working on this project for about 3 years. This is part of the MURI project in the United States. And one of our subgroup developed a flow-based model to describe this sea ice. And then basically it has the two equations. One is the displacement equation for each ice particle. So each of these particles described by like displacement by xi and then velocity. And this is a momentum equation, basically the Newton-Second law. And then on the right-hand side, there are features which captures, like, for example, the collision, the ocean and the atmosphere drag. This introduced the force. And then angular momentum and the fracture behavior, some welding and the freezing, some other features. So this particle method started in 1997. And then from there, there's a group of work done in Poland by Herman in 2011 and 2016 later on. And then there are many ongoing efforts in this direction. People found that it seems that particle method has some sort of advantage. We'll talk about it more. So the first question is how to represent the ice floes. So there are generally two ideas. One is to describe the sea ice as cylinders, or sometimes if we have a larger one, described as a bonded cylinders. So this is a main work described in this paper by Herman. And then here, this image shows that we took some image from a marginal sea ice zone and use some sort of softwares, and then it can automatically generate us like what are the appropriate cylinders to describe the ice. And then with this representation in this work, they successfully managed to simulate the fracture behavior of the ice sheet. So you see there are two fractures and behaviors captured very well. And then another way of representing the ice flows is by finite element. So in 2015, by Roberto, Latbe, and the rest, they describe each flow with 25 elements. So and then each element, we have to calculate the information of like displacement, velocity, this all the stress, or different type of things. So try to describe in this way. And then within our Muri team, a group from University of Washington, we describe the ice as the polygons. And then they call this model as the sub-zero model. So in this model, sorry, I skipped this video. So with this model, they more simulate the Nile Strait during a summer season where the flows are trying to get out of the strait. So let me try to play this video. I hope it works well. So as we can see here, the bigger flows start to fracture into smaller pieces. And then a very important feature they captured in this simulation is that this flow size distribution follows a power law. So this power law has been first observed from the image processing from the satellite images. And then once they're observed from the satellite images, then whenever we try to build the model, we try to capture this feature where we do the simulation. And so let's me, oops, okay. The video doesn't change, and let me try to, okay, so. Why is that? I'm sorry about that. I didn't expect this. Okay. Hope this works. Okay, so now let's take a look at the comparison between the continuum and particle models. So in the continuum model, it has a long history since 1979, about 40 years now. And then for the flow particle models, it has a shorter history since 1997, about 20 years. And then the continuum model has a reasonable accuracy on large scales, where the flow models can capture the small scales. So the difficulties on the continuum model is that this continuum assumption breaks down on smaller scales, where in particular in the marginal sea ice zone. While for the flow models, because we have to use lots of flows to capture the Arctic Sea region, the number of the flows is large. This brings the computational difficulties. So we were trying to answer this question here. Can multiscale models overcome these challenges, in particular to on one hand, we want to resolve some small scales. On the other hand, we want to try to reduce the computational efficiency. So we tried two things in the multiscale kind of discretization. Before that, let's take a look at the flow regime with the Knudsen number. So the Knudsen number has been defined as this fraction, meaning that it's a fraction of the mean free path of a particle, say in this case is a flow, over a representative physical length. So for sea ice, the regimes can be basically almost the larger part of this axis. So here in the small regime, hydrodynamic regime, when the Claudius number is small, in this regime, usually the flow is described as the Euler's equation, or more generally the Navier-Stokes equation. As the Claudius number increases, we enter the slip flow regime. In this regime, usually these models are described by Navier-Stokes equation. And then with larger ones, we have to add some particular conditions to the Navier-Stokes equation. Now we enter the transition regime. In this regime, usually the flows are described by the Bernard's equation. And then as the Claudius number goes larger, we enter this free molecular flow regime, where meaning that this particle's velocity is very high and it's trying to move around very frequently. This is usually for the gas dynamics. So this kind of model are usually described as the Boltzmann equation, either collisionless or with collision. Look into the PDFs, basically. So going back to the sea ice. So we have the regimes that, like, for example, in this marginal sea ice zone, we have many tiny small flows. And in this regime, that means that the Claudius number is relatively large. Where in this regime, this Claudius number is relatively small. So we have multiscale features just simply by looking at the Claudius number. And then what we want to do is we want to ask ourselves like how to efficiently represent these small flows, couple them. So the first work we tried is the superfloe parameterisation. So this is a recent work. The basic idea is that we certainly look into a Lagrangian reference or framework. And the idea is trying to treat a cluster of small flows as one superfloe. And the advantage is that it's significantly reduced the computational cost. So here, for example, we have a field of many flows. I believe this is 200 flows. And then we reduced it to 60 flows here, where the red circles represent the larger flows, the green circles, the small flows. All these small flows are clustered into superflows, which described as the blue cylinders here. So certainly there are properties we have to consider for the superflows, which I will talk a little bit more in a second. So test the model. So with this kind of idea, we look into what people call the discrete element model. This model consists of like basically the four equations. One is a displacement x, and then the velocity of each flow. This is one equation for each one flow. And the angular displacement is the angular displacement and this angular velocity, and the momentum and the angular velocity equation. Where looking into the momentum equation, and this is basically the Newton's law, right? And this term describes the fact of the flow collision. This term describes the impact from like the ocean drag or ocean force or atmosphere force. And similarly for the angular velocity part. So this is a very simple, cheap framework for some testing ideas like in data assimilation or uncertainty quantification or multiscale modeling stuff. And then going back to this superfloe parameterization, so what we did is that we have to pose some physical constraints where we try to generate these superflows. So again, we reduce these 20 flows into 30 large flow and 30 superflows. The physical constraints imposed here are kind of simple, and it tries to conserve the mass, concentration, momentum, and angular momentum. Those are the goals. And then we developed the algorithms trying to generate these superflows. So in the implementation side, by this simple structure, we found that using the superfloes can be treated very similarly as UV flows with some changes in the parameters, like for example, the Young's modulus for this superfloe. This superfloe is more easy to compress, so the Young's modulus is smaller with that physics constraints. So looking at the computational side, saving side with superfloe. So here, this blue curve shows the original full system with 200 flows. And then this red curve shows the superfloe parameterized system, 30 large flow and 30 superfloe. So we see a computational saving here. So looking at the statistics with the superfloe parameterization. So basically the main message here is that with the superfloe parameterized system, we can capture the main statistics of all the physics quantities like velocities in x direction or angular velocity, angular momentum, and momentum. So the PDFs are well maintained by this physics constrained superfloes. And then for a short time trajectory prediction on the looking into the uncertainty quantification. So we observe that this left side is showing the trajectories of all the flows in the momentum px in x dimension and the y dimension, and also the angular momentum. So all these uncertainties are well captured by the superfloe parameterized system. Well, if we do a simple kind of Baire truncation, then this uncertainty are much lower. So it's the uncertainty are not well maintained in the system. So the basic message here is that for short-term simulation, the uncertainty can be well maintained by using the superfloe. So looking into the data assimilation. So now data assimilation is kind of a tool to originally developed in the weather prediction and trying to give better weather prediction. And then this technique, this tool has been applied to other more like atmosphere or cloud related simulations or ocean simulations. So here in this case, since the Arctic sea ice region, it is the Arctic sea is covered by the sea ice, we would not know the ocean. We don't know where the eddy is and what are the things that are going on under the sea ice. So the idea is to look into the satellite images. We try to record the trajectories of the ice, and then take this model to predict the ocean current, the ocean eddy. So in this left plot, we can see that the most left columns is the truth, ocean current. This is the mode, the several mode. I think it is three mode here. And then if we use the superparameterized method coupled with the data assimilation tools, the particular method we used here for the data assimilation is called the ensemble common filter. We capture well the ocean mode. Similarly, if we look into a larger scale, larger region, so these eddies are captured well in the superfloe based method. So the message here is that this superfloe inflation algorithms capture well the ocean mode. So that's one idea of trying to balance the small scale and the larger scale through superfloes. Another one is now we take a look into the superparameterization on using both particle and continuum model. So the motivation here again is trying to capture both advantage of both the fine and the large scales. And the superparameterisation, which is developed for the particle-continuum model, originally in cloud science or like atmosphere, where the idea is that like in the Arctic region, they have a grid. So maybe you cannot see this grid; it's very small here. On each grid, they embed a fine-scale model for simulating the cloud here. And this fine-scale model interact indirectly with a coarse scale. So indirectly, so basically using like people use the time series of the data at this fine-scale model. And then each of this fine model can be parallel. They are kind of independent, only taking into the statistics for coarse scale dynamic. And then now in the sea ice, it is a little bit different. The difference being that for atmosphere and the ocean or cloud, they have one model. They only have one model, which is a continuum model on both fine and coarse scales. So one model for like more the classical multi-scale type of thing. In sea ice, we have basically two models. One is a continuum model on the large scales, on the coarse scales, and the flow particle model for the fine scales. The challenge here is that we see how to propagate the particle information, the small scale information, like especially like small eddies, and how can we predict with that, right? So the connection is from the distribution, the probability density function, where this F describe the flow sizes, the probability on the flow sizes and the thickness, velocity, and other many parameters. And if we take some integrations, then we end up with on the moments of the distribution. In particular, one example here is the mean ice velocity. That's the integrating over the velocity dimension. And then within our Muri project team, so this model was developed in NYU. The main idea is that look into this PDF pi and trying to decompose this probability density into some marginal and conditional densities. And then now we have basically two PDFs. And then the two PDFs separate the scale. One is the macro scale. This goes to the continuum model, and the micro scale goes to the particle model. So here, this model is super expensive, and this motivates us to develop the second model, which tries to capture the uncertainties from the ocean and atmosphere. Also, in the first model here, it's harder to encouple the contribution or uncertainty from the ocean or from the atmosphere. So here we developed a coupled model, a model which towards the coupling of the ocean. If we take a look into the figure, there are lots of interactions among all these components, like the ice, the ocean, the atmosphere, the cloud, the sun. So if we take a closer look at the comparison, the particle continuum model, the first model, looking at the Boltzmann equation, use particle cloud, and then it lacks the fine scale position, which gave us difficulties in the data assimilation, trying to capture the small eddies in the ocean region. And then the particle, the second model, we have a fine scale model, like each of these cells, we have one fine model. Say if we have an eddy, like inside one of these small box, then we can use this local fine scale model and then look into the density or concentration, the momentum. and then trying to integrate over like some momentums. And then we end up with this set of equations. So basically this is a Navier-Stokes type of equation where we have the information from the fine scale, which is this described as a stress tensor. And this stress tensor are some information we would gain from the fine scale model. So this will be used as an input for the continuum model. And then for the fine scale model part, which is the particle model, again, this displacement equation, momentum equation, which captures all the features in the particle model. And then the inference from the core scale is done through the the concentration rho and the velocities, flow velocity, like in the average sense or in the larger scale sense. So we will take the rho and the u to update, say, like flow radius and also the velocities here. So this is one part of the updating coupling procedure. So some preliminary result. So here, a simple setting, very simple setting. We're taking like about 10,000 flows, where we have all the flows. The ocean current is going to the right with a constant velocity, and the concentration is varying. The flow locations are randomly generated, and then we have high concentration in this region, low concentration in this region. And then in this simulation, we use a double periodic boundary conditions. And then this is a DEI model. When we apply a multiscale model, we look into the altitude norms, like the arrows, how the error decreases. So the message here in this plot is that if our larger scale model, the grid size is decreasing, then we have more accurate simulation, which is closer to the truth model. And then a more complicated case, which is we have a boundary layer on the right side. So for flows smashing to a coast, this usually a difficult simulation is in particular to capture the main features in the sea ice. With similar setting, like we have a constant velocity to the right, and then we use 41,000 flows with different varying concentration, different location, randomized location. So the multi-scale features captured multi-scale model captured the main feature. So in particular, if we look into the concentration of the flows, so we see that the concentration are kind of accumulated in the right boundary, also for the multi-scale model. So here we may observe some sort of diffusion type of thing or dissipation. This is due to things like core smash and the numerical solver we apply. We applied in particular here just first order time Martinsky. Now again, go to the errors. So basically this shows that the L2 norm errors roughly decrease linearly. So this convergence rate is linearly. This X shows the time. So we are still working on this, and they are trying to get the simulation faster, and then trying to have longer term trajectory convergence rates. So in the computational cost side, we roughly get 10 times faster when we're using 32 processors. So again, these fine scale models are all parallelized. They are all. And then other challenges. So one important simulation here is the case we have a gyre. So in the Arctic Sea region, there's a circulating gyre where it affects the fracture behavior, those kind of type of things. And we are trying to apply this multi-scale to simulate this, and then to see what we can gain the computational efficiency. Also in this case, which is the case which happens a lot when flows are going through streets like the frame street or new street. Flows can gathering and scattering. And let me move to the next slide. I hope it happens again. I'm sorry. So this slide shows, I have 2 more slides. So this slide shows that this is our team, CI simulate team, several institutes, and we work on different areas of the topic. Some people working like from Yale, working on the processing the satellite images, and then this institute working on the ocean coupling, and we are mainly working on the multiscale modeling part. And this comes to the summary. So I talked about particle and continuum models for describing the CIs, which with about 40 years of history in the continuum model and 20 years on the particle model. And then the multi-scale modeling part, we look into the superfloe parameterisation and then superparameterisation based on this. I will stop here. Thank you very much.
Any questions before? Maybe I'll just open up the start. So in the particle model, I'm just curious, if I just decided to represent CIs by the largest supercomputer that I could find, how big would the CIs be? So let's suppose I took the particle model into its absolute limit and through an XSL computer model. How big would a CI's particle be? Am I at the limit where I can actually resolve something at a reasonable scale, or is CI still significantly huge?
Yeah, so first thing is that it depends on the season we are looking to. Like during the summer season or winter season. So in the winter, all the flows are kind of going to.
Well, suppose I do it during the summer. Ice is smallest.
Yeah. In the summer, roughly these areas is about what 20 to 50 kilometers squared or something. I'm not sure 100% sure. I haven't checked that, but in the multiple. In this marginal CI zones, it can be very small, like it can be even can be few kilometers square.
Okay. So
in this
I guess what I was wondering, to take particle in its extreme and say, well, how many chunks of CIs can I model and how big would they be?
Yeah, so in my simulation, the largest number I did is like about 80,000 floes.
Okay.
Yeah.
So it's still
takes a lot of time. Like say, if I do about 80,000 floes and they say we want to simulate 3 months, that's in workload time, right? It's at least about a week's time. And still, also definitely depends on how complicated my model is. Or how much coupling I do. Yeah.
Thank you. Other questions?
Yes.
So there's a physical model or mathematical model that is somewhat close to non-Stokes.
Yes.
Is that model well posed? Can you say anything about well posedness of that model?
Oh yes, that model has been well studied, and it's developed from the Boltzmann equation by taking the integrations on the PDFs, and it has been very well mathematically rigorously established that from the Boltzmann equation to the Navier-Stokes equation, that has been very well studied, and yeah. So yeah, like these equations, yeah. So originally, this F has been used to describe the gas dynamics, like the gas